speaker, John Ramsey, and John is going to talk about neutron scattering by porous materials. Okay, so I won't alter the lights. It's always a pleasure to come back to Exeter on this special occasion, I think, to celebrate John's 90th birthday. It's a real special occasion. My links with Exeter go back to the early 60s. I came after Jim Castle. That was the time when Dick Gamage, who's nice to see here, Roger Bickley, Bob Breakspear, Frank Leach were working. I think I was one of John's younger boys here, and I think after my PhD, there were perhaps 2 more years when you had active PhD students. Maybe there were others when you retired, formally joined. But I really continued on doing some things which linked on with Jim's work, and at this particular time there was a lot of interest in gas phase corrosion, and Jim's followed that up very, very successfully. But the tail end of this program, which was financed by the Atomic Energy Authority, we thought perhaps we ought to understand a bit more the basic mechanisms involved of the corrosion process, the initial stages, and I was working on the interaction of CO and CO2 with alumina and magnesia, which at that time were canning materials in the first Magnox nuclear reactors. It seemed a very complicated system, in fact, at that time, and I think John Gregg's involvement there was very, very perceptive in bringing up lots of points which I think have been developed by many others afterwards. But there was lots of questions about whether one was looking at physical absorption, chemisorption. I think we're in the period when people were really realizing the important effects of micropores, this strong adsorbate-pore interaction, which has already been mentioned. Other aspects such as the validity of the Kelvin equation in small pores, were we dealing with fluids which were similar to the bulk state and where one could apply thermodynamic principles. In fact, I was a bit of a tearaway at that time, I think, because I got involved with infrared spectroscopy, perhaps to get more molecular insight into the structure and the mechanisms of absorption. Following on from that, there was interest in water absorption, and Norman Parkins has already mentioned this somewhat what appeared to be a disagreement, which was resolved, but essentially we were concerned with the mechanism of chemisorption of CO2 on alumina, and I think at that time techniques to characterize absorbed species, and we didn't really have detailed understanding of the microstructure of porous solids. So in that intervening time, I think one could went to Harvard with Professor Barrett after doing a PhD, but then I was attracted to go to Harvard with Peter Anderson and Ken Singh, but there's been advance in theoretical analysis, computer simulation, quite a high mass, and so that corresponds to effective wavelengths between 10 and 1 angstrom. Because of this mass, they have quite low velocities corresponding to that energy. This is the reciprocal velocity here, which can be measured using what are called time-of-flight spectrometers. So one can carry out energy resolution of the scattered beam after look at the energy after the neutrons have been scattered. This just shows an old research reactor. This is the Guido reactor at Harlow, where we have the core and the shielding, the D2O moderator, and out here we have instruments for measuring scattering processes. This shows a picture of the Pluto reactor, which is the same as the Guido reactor, which is now closed down at Harlow. There are more sophisticated research reactors, like this one at IRL, which are specifically designed to do neutron scattering. This is the reactor core, these are all the instruments around the core of the reactor. And one can collimate and monochromate the beam of neutrons. This shows the energy distribution of neutrons in terms of wavelength, and that's done using techniques like this. This is a chopper facility where one can monochromate the beam by rotating two slotted discs in this way. Okay. In incoherent scattering, there's one particular feature which is very important, especially if one's looking at water and hydrogenous materials, and that's the scattering cross-section of the atom, which for hydrogen is very, very high, and one can study in particular water absorbed in oxides, porous materials, because the contribution from the porous material is very low indeed. And with incoherent scattering, one can carry out this small angle scattering. One can attempt to do that by looking at the structure and the scattering of silica gels and other oxide gels as a function of water absorption in the pores. I mean, there are two extreme cases where if we have quite large mesopores, one could envisage in a silica gel which is made up of globular particles. This is based on the structure put forward by Karnikov. But if one has a silica gel made up of monodispersed spherical particles, one has a relatively uniform pore structure in the system, and then on the basis of this is proposed way back by Kislov, one can envisage, in the ideal case, capillary condensation occurring as shown here. In micropores, this mechanism breaks down. We have volume filling. Is there any practical way we can study that? Well, if we do small angle neutron scattering, what one can try to do is, in a mesoporous system where we have an absorbate, the solid, and the pores, we have three phases if we have partial filling in that particular case of mesopores. The two special cases where we have a two-phase system are where we have the evacuated porous solid or the pores filled with the liquid adsorbate. And in that particular case, the intensity of scattering, won't go into the details, is given in terms of these factors here which relate to the structure of the porous solid, and two terms which are related to the scattering length density of these two phases. So in this particular case, it would be the solid and the liquid filling the pores. If we
look at that, does to some extent, or to a large extent, I think, does depend on the nature of the precursor and the conditions of activation. And I think there is therefore room for further work and possible progress, indeed, by studying that particular aspect in more detail. On the whole, of course, if you take a uniform precursor, I mean, this is a great advantage of taking a synthetic polymer, as Brian knows, of course, rather than natural type of system, cellulose, you reduce the macroporosity enormously by doing that. And so I would have thought that's the kind of thing that might be well worth exploring.
Well, so it's at the side of our hands.
Yeah.
We have to rely on some expertise in this area. It's certainly that PVEC card there. It really is. It's almost on the verge of not being usable at all because the pores are so narrow.
Yes, fine.
If we could selectively widen those pores just by one molecule, we have really super absorption.
Well, in principle, I think you can.
Well,
can I ask a question about the economics of this? Because if the methane storage is going to be used on such a vast scale, you'll need carbon on a vast scale. And to talk of coconut shells, carbon, being produced in 10,000 ton quantities would envisage us all going away and investing in coconut plantations, I'm sure. It's just impossible to envisage coconut shell being produced in that quantity. So what ideas have you in mind for producing the appropriate carbons that can be compacted, because this is one of the densified in the right quantity? What kind of plans are there to produce them in this type of quantity?
I think what you say is undoubtedly true if you were talking about transporting gas and supergas tanker quantities. I think that's probably correct. But I mean, we are perhaps talking about a niche market here. And I think it can easily be done without distorting the present market. But in any case, the whole thing will be self-regulating by the cost. If it's going to cost that much, then you're not going to penetrate the market. So I mean, that's a question a lot of people raise, but it's not at the present moment a question for which it causes us too much loss of sleep. Putting the thing the other way around, we had an open day, press day recently, and in fact British Gas got a lot of credit for encouraging the economics of the developing world countries who supply all this coconut carbon. So I think at the present moment that they'd be quite delighted if more of it can be used.
See, Columbia Gas in Michigan are going around with their cars driven by methane that's absorbed in these cylinders, and
I think
they're looking for much larger quantities than they can presently
Perhaps
envisage.
perhaps that question is best resolved in the bar. If it could be resolved. Are there any further questions?
Well, a question to David Nicholson is whether he gave us two models which were essentially cylindrical pores and sheet-like pores, and I wonder whether you considered what happens in the alternative, I think a little bit more complicated system of the pores left behind by the aggregation of spheres, which came into the latter part of the discussions. Have you considered that, David?
Well, I mean, there are various ways you can approach more complicated models. I mean, in the simulation, we've tended to stick to very simple geometries like slip-shaped pores and cylindrical pores, because one of the things I hadn't mentioned is that you're only using a few hundred molecules and at the most a few thousand molecules in the simulation even these days. I have made a step along that road in that I did some work with one of my PhD students in which we used a model where you have a spherical section joined by two cylindrical sections. And so actually the thing that we were primarily interested in there was transport properties, and we wanted to see how this type of geometry affected transport. So that's one way to go. I mean, the other thing that you can do is to build these very basic sort of elements into network structures and join them together. So once you know how the basic element behaves, you can then start joining those together. And of course, as far as adsorption is concerned, as far as the adsorption process is concerned, it doesn't matter too much how you join them. When it comes to desorption, then the network properties become important too.
I think I'd better draw it to a close there, because it's almost 6 o'clock, and some of you got a book in Berg.
Guest of honour, and Professor Toast, and to wish him all the very best for the birthday. Good wishes, and thanks for everything. John, thank you. And the next thing is to ask Peter, who will read out